Good afternoon, and thanks for your presence here today, and thanks to Assocarta as well for hosting this conference. My name is Alan Carnevali, and I work for Renovis. Renovis is an energy service company, and we deal with the realization of technological systems that help our customers to make their production process more efficient, increasing the overall efficiency and reducing the consumptions and the emission as well. As you have heard the distinguished speakers before me, explained how challenging and strategic the achieving of carbon neutrality by the year 2050 will be, and also how technology can help us in this path to energy efficiency and carbon footprint reduction. In the same way, and for the same purpose, I would like to present you the results of an ambition project carried out by Renovis at the Italian plant of Kimberly-Clark Corporation, settling in Romagna Sesia, nearby Novara. The implementation of a system that recovers the thermal energy contained into the exhausted fumes coming out from the steam generator placed downstream the existing turbogas plant. Said energy would be otherwise normally dispersed into the atmosphere. In this first slide, and in the next one, we can see the current layout of the turbogas plant. In particular, we can see the gas flow available downstream of the steam generator and its temperature that is more or less 170 Celsius degrees. This combined cycle plant can deliver an electrical power of 17 megawatts and produce approximately 24 tons per hour of steam, of which approximately 1/3 is made up of make-up water. To accomplish the project, we created a new ductwork, as you can see in this slide, to divert the fumes coming out from the steam boiler to the fumes water heat exchanger that we designed, built, and then installed on site. The exchange of energy takes place into the heat exchanger, and it allows us to obtain a thermal power of 5.5 megawatts in the form of water at a temperature of 90 Celsius degrees. Recovering thermal energy from the fumes obviously means that they undergo a cooling down to about 78 Celsius degrees, and they are then expelled into the atmosphere by means of a new chimney, specifically built for this purpose. The hot water generated through the heat recovery is stored into two inertial tanks of 15 cubic meters each. Their function is to temporarily separate the production of hot water by means of thermal recovery from its use, optimizing efficiency of the overall system. This slide summarizes the saving results obtained from the first phase of implementation of the thermal recovery system we designed and built. The total savings for heating the semi-finished product storage warehouses and for preheating the make-up water of the recovery steam generator is approximately 2,400,000 standard cubic meters of natural gas, corresponding to approximately 4,400 tons per year of avoided climate-altering gas emissions. As we shall see, part of the hot water produced by the system is used to feed an absorption chiller, and its installation, which is currently being in completion phase, represents the second phase of this project. Thanks to the chilled water produced by the absorption chiller, we are able to optimize the efficiency of the gas turbine. In fact, in this slide, we see how temperature of the inlet air entering into the gas turbine affects its performance. In summer, the high temperature of the intake air produces a significant drop in the performance of the gas turbine. However, this phenomenon can be avoided by cooling the inlet air by means of a chilled water air heat exchanger located in the intake chamber and supplied with cold water produced free of charge by the absorption chiller I mentioned before. We can see, particularly in the diagram below, how the curves of electrical power output from the gas turbine diverge as the temperature of the incoming air increases, depending on the presence or absence of an air pre-cooling system. The green curve, of course, represents the operation of the turbine in presence of a pre-cooling system, and we can see that, on average, the installed system allows us to recover from 1 to 1.5 megawatts of electrical power produced. Hydraulically, our system is very simple. The hot water at 90 Celsius degrees generated by the heat recovery system, I mentioned at the beginning, is directed to a distribution substation from which it is diverted, depending on the season, to the heating systems in winter or to the absorption chiller in summer. In this slide, we see exactly the hydraulic pipeline branch that feeds hot water towards the absorption chiller. The absorption chiller, based on lithium bromide technology, generates a cooling capacity of 1,900 cooling kilowatts. The chilled water produced by it at a temperature of 7 Celsius degrees is then pumped to the specially designed cooling coil installed in the intake chamber to drastically cool down the air entering the gas turbine. We are able to subtract almost 20 Celsius degrees from the air entering the gas turbine, bringing the gas turbine operating conditions back to nominal. That is more or less 33% of efficiency in energy production. The absorption chiller, which is based on lithium bromide technology, generates a cooling capacity, as I said, of 1.9 megawatts of cooling power. This means that it is able to bring the efficiency of the gas turbine back to nominal condition, as I said before, even in summer, and therefore without the ambient air temperature harming performance. So the performance remains the same during summer as in winter. We are therefore able to obtain from the gas turbine an additional power of more or less 1,500 kilowatts of electrical power from the cogeneration system, of course, even during the summer season, of course, if compared to the absence of a cooling coil system in the inlet air chamber. This means a real optimization for the plant. We can produce more or less 4,700,000 more kilowatts per hour of electricity per year and avoid greenhouse gas emissions of about 1,100 tons per year. Our project finds its conclusion finally with the second hydraulic pipeline branch that delivers hot water to another large department of the plant that is heated with heat during the winter season. This allows to obtain further savings, nearly 300,000 standard cubic meters of natural gas, avoiding harmful emissions into the atmosphere of more than 500 tons per year. In these slides, you can see some pictures taken from the plant we built. The first one is, of course, the turbogas system realized by solar turbines, while in the second and the third slide, we can see the air duct realized by Renovis for the intake of the fumes coming out from the steam generator, and at the bottom, our thermal recovery system. I take this opportunity as a conclusion now to briefly tell you about another project that Renovis is developing, the recovery of waste heat from the paper machine. Heat recovery from paper machine should be a usual good practice in order to down paper, making energy costs radically because the system reuses heat to replace primary energy sources. From the paper machine drying section, it is possible to obtain a significant amount of thermal energy through the recovery of the sensible and latent heat contained in the exhaust smokes resulting from the process itself. This slide shows us, in fact, how significant are the flow rate, temperature, and humidity of the fumes coming out from the drying section of the paper machine. In our project, existing paper machine dryer sections exhausts are connected to the heat recovery system. This last is configured in 3 subsequent smoke water heat exchanging stages. The first stage generates superheated water in a closed circuit at 110 Celsius degrees, which returns to 90 Celsius degrees as end cycle temperature. The recovered thermal power is 2 megawatts. The superheated water is used to power an organic Rankine cycle turbine to produce electricity. The second stage instead delivers hot water at a lower temperature, useful for the felt-forming section of the paper machine itself. The thermal power developed in this stage is about 230 thermal kilowatts. By means of the third and last heat exchanging stage, we can produce hot water to be used in the pulper as well. By means of the third and last heat exchange stage, we can produce hot water to be used in the pulper in form of hot water at not more than 45 Celsius degrees. The thermal power obtainable is really significant. As you can see, it touches almost 8 megawatts of thermal power recovered. I will now conclude my presentation by showing you the estimated results that can be obtained from the implementation of this project. As you can see, it is possible to produce a significant amount of electricity and save an important amount of natural gas by means of the plant we'd like to realize on paper machines such as the ones operating nowadays in Kimberly-Clark Corporation Italian plant. We can save more or less 1,700,000 of kilowatt per hour yearly, and more or less 230,000 standard cubic meters of natural gas. Renovis is working tirelessly to implement projects such as those presented today. Our activity is aimed at the whole industrial sector in which paper production is at the top of our attention. So I thank you for your attention, and if you have any question, please visit us at stand number 155, and we'll be very happy to answer to all your questions. Thank you.